All right, so let's go ahead and let's start with our problem number 3, linear viscoelastic materials. So I'm trying to model viscoelastic material. One of my undergraduates drew this, or is proposing this SLS below. So constitutive equation for the model, stiffness, short times, long times, what would the creep values be at short times and long times? So let's go ahead and look at and draw this material. So if I'm looking at time t equals 0, we know that we can treat effectively, we could treat our model or our dashpots as wires. So at times t equals 0, pulling infinitely fast, we would look and we'd have a model that looks like this. So we'd have this E1, and then flat, and then done here. So there would be some stretching in that E1 wire, but our effective stiffness essentially would be infinite, because again, this is not going to strain, so it'd be infinite here. If I do times equal infinity, they are basically disconnected, so our model would look as such. So I'd have this, my E1, completely disconnected from here, and then disconnect, everything. Everything is essentially dead. So there's the effective stiffness here would be, would be 0. E would be equal to 0. So that's how the model looks like. Now, it asks us to consider what would essentially the creep behavior be at these long times and short times. So if we remember, what are we doing when we're doing our creep experiment? So in our creep, we are doing our stress is equal to a constant value, so we're looking at essentially our strain. So our strain is a function of at very short times for this model. So strain as a function of time would look as such. So at very, very short times, the strain would be effectively 0, and here the strain would be kind of basically almost infinite up here. So you pull and just it'd be instantly going off. So not the best model, and that's why, again, my undergraduate students proposed it. Not that they're not brilliant and geniuses, but so it's not the greatest model to kind of model the behavior that we're looking for. Which is, if you remember, we always want, we expect essentially real materials. If I do a stress relaxation test, I should expect my stress as a function of time or temperature to look, again, like our viscoelastic materials. So we know that for viscoelastic materials, as we pass TG, time temperature equivalence, we should see something like this. And the strain would be the opposite. So we'd have basically low strains at low temperatures, and then basically a plateau. So that's the behavior we're looking for. This is not it, but we can kind of still continue to work with this model. So I need to write out the constitutive equation. So I know that this first arm is what? You guessed it, my Kelvin Voigt. And then in my second arm here, this is just going to be my E dot of my 2 arm is going to be, actually, excuse me, let's do our stress in the 2 arm. Our stress in the 2 arm is going to be equal to our eta 2 times strain rate of that 2 arm. So let's go ahead and let's write out the constitutive equation. So if I'm looking at the, this is not Kelvin Voigt, excuse me. My apologies. This is my Maxwell model. So if I'm looking at my Maxwell model here, and if I look at this system, the Maxwell arm, I'm going to shorten that as M, and if I look at this second arm here, I know that they are in parallel, so they're not in series. So I know that the strain of my SLS must be equal to the strain in my Maxwell, which must be equal to the strain in my 2 arm. Equivalently, I know the strain rate must be equal as well. Strain rate of 2. Fantastic. Now, that's great. I also know that the stresses must sum. So the stresses in my SLS must be equal to the stress in my Maxwell plus the stress in my Maxwell plus the stress in my 2 direction as well. So those are the relationships that we're going to be working with here. So now we need to write essentially a constitutive relationship. So let's start with this guy. So this will stay, and I know stress in the 2, I've already got it here. So my stress in the 2, I could rewrite this as eta 2, and then again, because this relationship holds here, I could rewrite this as epsilon SLS. So I could plug that in whenever I want to for sigma 2, and I have everything written in terms of my standard linear solid model. Now, for the Maxwell, I need to start to consider rewrite this, essentially the expression. So way back, and I'm going to zoom out here just a little bit. So I have the following expression for the strain in my Maxwell model is going to be equal to the stress in my Maxwell model dot over my basically module here plus, I'll do this sub 1, plus my stress in the Maxwell over my eta 1. Alternatively, I could rewrite this also a little bit more simple. So I know the strain rate of my Maxwell from this expression here. I could write it as the strain rate of my standard linear solid, and then the rest of this remains the same. Dot over E1 plus M over eta 1. Now, here I have the issue and the problem really of I need to rewrite this in terms of the stress of my Maxwell model because I want to plug this in. Again, I have this component here. I've already checked off this guy, so I need to rewrite this equation. So I'm going to do that and do that up here. So my stress of my Maxwell is going to be equal to basically stress Maxwell is going to be equal to strain rate of SLS minus my strain rate or stress rate of my Maxwell over my E1, and all that is going to be multiplied by that eta 1. So eta 1 and then eta 1 here. So I've got this expression now. Fantastic. So I'm going to plug that in right here. Now, I still have a problem. This guy right here. So I need to basically rewrite this relationship and say that my stress rate of my Maxwell is equal to the stress rate of my SLS minus the stress rate of my sigma 2. So I can go ahead and do that, dot that function, and what I'll be left with is the following relationship. So this will give me that sigma dot Maxwell equals sigma dot SLS minus my eta 2 epsilon double dot of my 2, and my epsilon 2 is also the SLS. So I can now combine all of those expressions and zoom out a little bit more. So my final expression is as follows. So the stress of my SLS is equal to, I'm going to write this expression again, sigma m, right it here, eta 1 strain rate SLS minus, I'm going to plug in this expression here for my sigma dot m, minus my sigma dot SLS minus my eta epsilon double dot of SLS. That's all for this guy right here. This is all over E1, eta 1, and then now I'm going to also add my sigma 2, which is plus, where's my old friend sigma 2, eta 2, and this eta, excuse me, this must be eta 2 here, eta 2, excuse me, let me erase this, plus eta 2 times my epsilon dot SLS. There we go. We've got it. So that's all our solution. So I'm going to erase everything now. Hopefully you pause the video. And again, someone please tell me, how do I do a massive erase? Is there like a huge way to just do a huge eraser? Anyways, in the comment section, help me out. I'm too lazy to learn, the nuances of that. But anyways, we'll figure it out. All right, so now we're given some dynamic mechanical testing experiments. So I want to be able to calculate the relaxation time of these three polymers. So I have the G prime. So I'm looking for this crossover point. So I'm going to put this one, yeah. So I have this crossover point. Actually, do different colors. For this polymer, it's this crossover point. For this polymer here, I see a crossover point right here. And then for the other guy, I see a crossover point right around. So let's go ahead and write these. So each of these are reaction frequency. So this is our angular frequency, but we need to convert into cyclical frequency because we want the relaxation time. So we know that omega equals 2 pi f. So if I want frequency, which is going to be in hertz, and I'm going to convert hertz to seconds, I could do cyclical frequency equals omega over 2 pi. And I have those three omega values. So I could go ahead and start to solve for this. Let's use our Mathematica notebook we've been using previously. I don't know if you could hear the leaf blower outside, but let's go ahead and figure these out. So our omega B for black is going to be equal to 1. Our omega, I'll do omega black. Our omega blue is equal to 10, and our omega red is equal to, let's zoom in a little bit here. So if we look over here, it's probably more 20, 30, 40, 50, 60-ish. Let's just say 60. So let's go 60. These are all in, again, radians per second. So I need to, my F black equals, again, W black divided by 2 times pi. Let's look at this numerically. We can do the same thing for F blue, F black, and then F red equals, well, not F black, oops, W blue, and then frequency here, F red equals W red. So now I could do 1 divided by F black, because again, that's in units of basically hertz inverse. So if I take the inverse, that's going to be second. 1 over F black, 1 over F blue, and then finally 1 over F red. So does this make sense? So this is the relaxation time. So let's look at these polymers. So I'm looking at frequency. So at very, very high frequencies, I'm looking at these values, my G prime, my storage module should dominate. Okay, so that makes sense. At very, very, very low frequencies, that should dominate as well. So if I'm looking at the relaxation times of my polymer, the relaxation time for red is very, very, very small. So it should have the lowest TG. So again, if we were plotting this in terms of time, in terms of temperature, for example, this would correspond to a very, very low temperature here, and this would correspond over here to a very, very high temperature. So you can kind of correlate those properties too. So if I'm looking at that, that has a very, very, very low TG, or glass transition temperature essentially. So that will kind of correlate those values. So we are being asked, so we've calculated the relaxation times of the 3D polymers. What times will the polymer behave like a solid and a liquid? And then viscoelastic fluid. How do you characterize the backbone stiffness of the polymer? So first, we can answer that question. How will we characterize the backbone stiffness? So if I have a very, very, very small relaxation time, it means that the polymer can basically relax back instantaneously. If I have a very, very long relaxation time, then that means, if I have a very, very, very long relaxation time, then I'm looking at a polymer that it takes a while for them to form back. So we can kind of see here, this is a very, very low relaxation, or you can also think about this in temperature here. So low temperature here. So my TG, or the glass transition, when we switch from viscous to elastic, all those good things. So very, very low glass transition temperature, higher glass transition temperature for the black guy here. So I know that my TG of my black is greater than the TG of my blue is greater than the TG of my red. I also know that my relaxation time, my tau of my black, is also larger than the tau of my blue. It's greater than the tau of my red. So makes sense. Longer relaxation time, the longer it takes the material to relax back. So I know that this black molecule probably has, again, it may have some very, very stiff molecules in the backbone. It could have these styrene rings. It could have some intermolecular interactions here. So I could have H bonding in my backbone. I could have long pendant chains that have the styrene groups, et cetera, et cetera, et cetera, et cetera. So for the black material, I'm going to have very, very, very stiff bonds to the backbone. It is going to be very difficult to rotate around those bonds, and I could have intermolecular interactions. My red one, on the other hand, it is essentially going to behave much, much more viscously. So I have materials essentially that can there's very, very flexible backbones, easy to rotate around the bonds, and then there's probably very little to no intermolecular interactions. So that's the characterizing the backbones intermolecular stiffnesses. So high intermolecular interactions for, high intermolecular interactions for this guy right here, low intermolecular right here, high bond stiffness here, low bond stiffness right there. Now, we're asked to say what experimental times will our polymer behave like a solid or liquid? Well, we know that my Deborah number, which is equal to number equals my relaxation time on my polymer over the experimental time. So we've said before, if I have a polymer with a very, 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 very small relaxation time. So if my relaxation time is extremely, extremely small relative to my experimental time here, my Deborah number, will be much, much, much less than 1. If I have a small relaxation time, it means my polymer, just like we calculated here, small relaxation times mean I could adapt well to perturbation. So I'm going to have a much, 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 much lower TG, and I'm going to be much more flexible, and I could kind of rig around. So if I am much, 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 much less than 1, then that material is effectively going to relax instantaneously, and this could behave similarly to a viscous polymer or even a fluid. So we have a way that we can kind of characterize this. So if I'm much, much less than 1, I'm going to behave like a liquid. Alternatively, you could think of it in terms of experimental times as well. So if my experimental time, if I'm pulling something very, 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 very long, my Deborah number is going to be very, very small. And if it's much, much less than 1, we're saying it's basically less than 0.1. Alternatively, if my Deborah number is larger than 1, i.e. 10, that means my experimental or my relaxation time is very, very long, meaning it's difficult for my polymer to respond to perturbation. Thus, I should expect this to behave like an elastic solid. And linear viscoelastic materials or viscoelastic materials will fall in between there. So I've got my relaxation times, so now I can kind of solve for these values. So this is my, I'm going to say T black, or tau black, this, my tau blue equals this, my tau red equals this. So now I can go and start to work with this material. So I want to solve, my Deborah number is basically my tau black divided by T, and I want to solve when this is equal to 0.1. So this is the experimental time when this is equal to 0.1. So what we're saying here, so if this is 64, if it's larger, you get, let's see, is this less than 0.1? About 80. So if I'm looking at experimental times larger than 62, I'm going to behave basically like a liquid. If, and you could do the same thing, we could do the same exercise for the other ones. If instead, if my times are shorter than 0.62 seconds, so for example, tau black divided by 0.5. So if my experimental times are smaller than 0.62, I'm going to behave like an elastic material. And in between those times, I'm viscoelastic. And you could do the exact same thing for tau blue, and tau red. Excellent. That's it. Now, we're finally told that we need to, for each of the polymers, sketch the curves for stress and strain and stress as a function of time for a KV creep experiment. So we need to, again, have those equations handy for my Kelvin-Voigt and those models. So for the Kelvin-Voigt model, I know for a creep experiment, I am applying a constant stress. So luckily, we know that this plot is going to look the same for all the materials. So constant stress, sigma naught, and then I measure my strain, which is going to be equal to my sigma naught over E times 1 minus exp minus T over tau. So I know in general the curve should have a shape as follows. So what happens at my experimental time T equals 0? So exponential of 0. Let's go ahead and do that. Remind ourselves. Exponential of 0. It's 1. 1 minus 1. So we start here, and then we'll asymptotically increase to a certain value here, which is basically this value. Because if I look at exponential of minus infinity, will eventually be 0. So this asymptotic value will be sigma naught over E. So when I'm trying to draw this for each of the curves, what's changing here? Well, we know that my Young's modulus is probably changing. And Young's modulus, roughly, we should expect it to kind of scale similarly to our TG. So the higher the TG value, the higher the stiffness. In general, you might kind of expect it. So we're going to see this value, this y-intercept, essentially change for the polymers. And we'll know that, again, this value will be much lower. So for example, let's go ahead and change color. So for my black molecule, it'll be basically right here. And then for my red molecule, let's go back to our favorite. For our red, it'll be essentially higher here. So that will shift essentially your curve in this asymptote, and thus kind of the shape of this curve as well. Similarly, let's look at these exponential values. So we saw, for example, let's look at for any given time. So exponential minus, let's say time 1 second divided by my tau black. So that will be, we can look at this 1 minus value, and then we can do the same thing for red. So we actually see quite a bit of a difference, right? So it's basically going to be almost 1. So it's going to be, so as we kind of see here, our red curve is going to reach that asymptote much quicker. So our red may look like this, asymptote here. Our black curve may take a longer time to kind of a smaller slope to reach that value. So longer times. So there we go. That is our problem 3. So let's get into the last problem, problem 4. See you in the next video. Thanks.